So today we're going to look at some more application problems for our quadratic function. We looked at some application problems yesterday with that baseball example, and we're going to look at some more today. When we start to talk about applications for quadratic functions, a lot of the problems that we're going to look at are going to be some sort of projection. So we had the baseball examples from yesterday. We hit a baseball and we're looking at how does that baseball travel. Our first example for today is going to be a golf ball. So same idea. This time, instead of hitting a ball with a bat, we're going to hit it with a golf club. But projectiles are really great examples of quadratic applications because when we look at the time that that projectile has been in the air versus its height, we tend to see a pattern that looks like this. We tend to see a quadratic pattern, right? It rises, it reaches a peak, and then it comes back to the ground. I launched a rocket or I threw something. That all tends to be a quadratic function. So if we take a look at our first problem here, it says Jennifer hit a golf ball from the ground and it followed the projectile path described by this function. So it's a t-squared function, the quadratic function. T is the time in seconds after she hit the ball, and h is the height of the ball in feet. So we want to find for this golf ball the highest point that it reaches. So how high does the golf ball get? And then when does the golf ball come back to the ground? Now we're going to use our function that we've been given, and we're going to use our calculators to create a graph and answer these questions. But before we do that, I want to take a minute to stop and think about what it is we're going to look for once we've graphed this function. So type this in, graph it, great, we have the graph, but now what am I looking for on that graph? So what am I looking for the highest point that the golf ball reached? What key feature on the graph are we going to be looking for? Highest point the golf ball reached. That maximum height. What's the highest point on my graph? Okay. For a quadratic function, that's also what we call our vertex. So we're going to look for the maximum or the vertex here. And then I want to know, when does the golf ball come back to the ground? When does the golf ball hit the ground? What's that going to look like on the graph? Yeah, and we looked at this yesterday with our baseball problem, right? When does the baseball hit the ground? This is going to be our right side x-intercept. So now that we know what we're looking for, let's go ahead and graph our function on our calculators and find those key features. So let me pull up my calculator here. I'm going to add a graph page. And then as I type this in, the function on my paper uses t. But remember, our calculator is set up for x when we're graphing. So anywhere I see a t in my function, we want to make sure we put an x. So this would be negative 16x x squared plus 100x. Okay. And this doesn't look like a parabola, right? It looks like two vertical lines because my parabola is very tall and skinny, and so my maximum is going to be way up here somewhere. So when we looked at problem graphs like this yesterday, we needed to adjust our zoom to be able to see the whole parabola. We're looking for just the maximum on this graph. We actually don't need to be able to see the maximum to get our calculator to find it for us. So I'm not going to adjust the zoom on this. I'm going to go straight to menu, analyze graph, and my vertex is a maximum here. So I'm going to select maximum. Now, as a reminder, when I'm trying to have my calculator find key features, my goal is not to try to click on, with my dash line, click on that feature, right? I don't have to try to do that. My calculator can do that work for me. I know that the maximum should be in here somewhere. So what I'm going to do is click on either side of where I think that maximum is going to be so that I capture it in that shaded region. And then when I do, my graph zoom adjusts for me here, and I can see that maximum point. I'm going to jot this down on my paper. Our vertex or our maximum is at 3.12, 156. Okay, and then I'm going to put my calculator away for just a second. Now, question A says, what's the highest point that the golf ball? So how high did the golf ball get? That's the question I want to answer. This ordered pair is not the answer to that question. I'm asking about height. I want to know what was that maximum height. So I want to just give that height portion. Remember the y coordinate is our height. So what's the highest point the golf ball reached? How high did the golf ball get? It got to a maximum height of 156 feet. Just that y coordinate. And now I'm going to go back to my calculator. And we want to find that right side x-intercept. That's kind of hard to see with my graph zoomed out this far. Right after I hit enter, and we had our graph that just kind of looked like two vertical lines, we could see that x-intercept. So I'm actually going to adjust my zoom back to that original screen. So I'm going to hit menu, and then I'm going to go down to window zoom. We've dealt with zoom in and zoom out. We did zoom fit. Zoom standard takes us back to the original screen. That's the one I'm going to select. Always good to know how to get back to that original screen. So I know I want this x-intercept. That's when the golf ball hits the ground. I'm going to go to menu, analyze graph, and then I want 0. That's calculator speak for x-intercept. And then again, I don't have to try to land right on it. I want to click on either side so I get it in that shaded region. And then I can see my x-intercept. So it looks like 6.25. 6.25 comma 0 is my x-intercept. Remember, I don't want to answer the question with a coordinate, with an ordered pair. I want to answer the question in the context of the problem. So it says, I want to give the time the golf ball returns to the ground. The golf ball returns to the ground 6.25 seconds after she hits it. Questions for me on our first problem here? Okay, let's take a look at number 2. For number 2, it says the profit for selling local ballet tickets depends upon the ticket price. Using past receipts, the profit can be modeled by this function where X is the price of each. Profit functions or revenue functions are also typically quadratic models, quadratic functions. As we set the price for something, that price is either going to encourage people to buy whatever I'm selling or discourage them from buying. Now, my price should cover the cost of the materials to make my product, as well as any other cost associated with selling my product. And then it should also include a little bit of profit for me, for everything that I sell, every item that I sell. If I price my item so low that I make very little profit, a lot of people may buy it, but I'm not making much money. On the other end of the spectrum, if I price my item so high that I make a lot of profit on each individual sale, it's probably priced high enough that not many people are going to buy it. So I'm not going to make a lot of money because I'm not selling a lot of this product. In between those two extremes, there's a sweet spot, a middle ground, where my item is priced so that many people will buy it. And I also make a fair amount of profit on each item that I sell. So because I'm selling a lot of them, I make a lot of money. So that looks like, when I look at the price versus the profit, that looks like, again, a parabola. It looks like a quadratic model. And the goal for most companies is to find that sweet spot, right? They have somebody literally do the math to figure out what should that price be so that we can make as much money as possible. So that's what we're looking at here with our ballet ticket sales. So we want to know, what's the ticket price that gives us maximum profit? And then what is that maximum profit? And then what ticket price would result in the local ballet breaking even? So we're going to graph our function. But before we do, again, I want to stop and talk about what am I going to look for on that graph. So that ticket price that's going to give me that maximum profit. What key feature will I look for on the graph? The vertex, yeah, the vertex or the maximum. And then for C, what ticket price would result in the local ballet breaking even? So breaking even means that we have a profit of $0. We haven't lost any money, but we haven't made any money either. That's breaking even. What key feature will I look for on the graph to see where my profit is 0? We could use the table. If I talk about the graph, like what point am I looking for on the graph? Or if I use a table to find it, how will I know I found it? Remember, profit is our y-axis. So I want when the y is 0. Where is that on my graph? When y is 0. I'm looking for x-intercepts, yeah. Okay, so let's graph our function and then take a look at those key features. Let me pull up my calculator. And I'm going to make a new page here. And let me graph my function. So negative 15x squared plus 600x plus 60. And again, I don't have a great picture of this because it's such a big parabola. So I'm going to adjust my zoom here. So let's go to menu, zoom, and we'll try a zoom fit. I can start to see that curve. I can't see the maximum yet, though. I can't see the other half of my parabola. So we'll zoom out a little bit. Menu, zoom out. There we go. Okay, now let's find that vertex. So this is menu, analyze graph, maximum, since the vertex is the maximum point on this graph. Uh-oh. Oh, hang on, let me bring my calculator over here really quickly, see if I can undo whatever I just did. There we go. Okay, take 2. Menu, analyze graph, maximum. There we go. Okay, so I'm going to adjust this on my paper. I got 20, 6.06 E plus 3. What does E plus 3 mean? Yeah, it's scientific notation. This is your calculator's way to represent scientific notation. So let me put this away for just a second. So in middle school, when you learn to write scientific notation, you wrote this as times 10 to the whatever power. So since it's plus 3, this would be 10 to the 3rd. And what that means is that you want to move your decimal 3 places to the right because this number is bigger than what we're representing here. So 1, 2, 3. So we would get 6,060 as our y value. Anytime you get an E, that's your calculator saying I'm giving you scientific notation. If it's plus a number, that means that your number is bigger than what you're seeing here. If it's minus a number, that means you're going to move your decimal the other way because it's smaller than what you're seeing. Okay, so scientific notation. So to answer my first question, what's the ticket price that gives a maximum profit? I want to know the ticket price. Remember, that was our x coordinate. So my ticket price would be $20. And then part B asks, what is that maximum profit? That's the y portion. My maximum profit is $6,060. Questions for me so far? the 20 comma blah, blah, blah. So on my calculator, there we go. I went to menu, analyze graph. And since my vertex is the maximum point of my graph, I did maximum. And then we click on either side. Now, the other key feature we need to find is the x-intercept. So we're going to find this x-intercept over here. Menu, analyze graph, 0. Remember, 0 is my x-intercept finder on my calculator. And so this one looks a little weird too. I would expect for the x-intercept to have a y value of 0. Instead, what I have is negative 9.9 e to the negative 10. I'm finding the right one. Our y-intercept for this thing is 60. I know that because we have standard form. And remember, standard form gives us the y-intercept. So my left side x-intercept would actually be negative since our y-intercept is a positive number. So I'm going to look at this right side x-intercept. So I would expect this to be 0. Instead, it's scientific notation again. And because it's e negative 10, that tells me I'm moving the decimal really far this way. So it's a very, very small number, really close to 0. For our purposes, there are some settings that we could manipulate on our calculator so that we don't have what I'm going to check this up as a rounding error. For our purposes, I'm not going to worry about fiddling with the settings so much. I care that you know that we're finding a 0 and that we want the x-intercept to answer this question. So I'm not going to worry about messing with the calculator settings so much. But I want us to recognize that this is a very, very, very small number, very close to 0. We're not getting exactly 0 because of some settings. There's some rounding issues. Okay, so that x-intercept would be 40.1. I'm going to jot that down on my paper. So 40.1. And the question I'm trying to answer is what's the ticket price? So because I'm answering a question about a price, I'm going to rewrite this as $40.10. I'm going to put the 0 there because we're talking about money, and for money, we round it to decimal places. Questions for me on problem 2? Okay. We have one more problem. We have one more problem we're going to take a look at for today. So on the very last page of our notes, problem number 3 says a kicker kicks a football in an attempt to make a field goal from 105 feet away from the uprights. The uprights are 14 feet high. The football reaches a maximum height of 75 feet when it is 50 feet from the kicker. And then we've got a diagram of this information. This is very similar to the baseball problem that we looked at yesterday. So yesterday for our baseball problem, we were hitting our baseball from home plate, so many feet away from the green monster. We knew how tall that wall was, and we were trying to see if anybody hits the baseball over the wall. This is the same idea, right? But this time we're kicking a ball instead of hitting it with a bat. And our distance is a little different, but I'm trying to get it over the goalpost, right? I want to get it over the upright so that I can score this field goal. So our question is, did we do that? Okay. Now, this problem's a little bit different than the ones we've seen so far because we don't have a function that describes this. We've got some important information here. We've got some distances. So we know the vertex of our parabola. We know where we started. We know the height of those uprights. We don't have a function that describes this. That's actually what we're going to do. We're going to create the function on this one, okay? So the nice thing for this problem is that we know the vertex. You know the vertex is 50, 75. Since I know the vertex, I can almost write vertex form. Now, I say almost because the important piece of information that we're missing right now is the lead coefficient. We don't know what our lead coefficient is just yet, so I'm going to leave A in there as a placeholder. And then I'm going to write the rest of vertex. So that would be X minus 50 squared plus 75. I know almost all of vertex form. Now, based on the shape of my parabola, I know that the lead coefficient should be negative, but I don't know the value. So is it -1? Is it -5? Is it -0.0842? That's the part I don't know. But we can figure that out because we know another point on this parabola. So since I know another point on this parabola, I can actually plug in these x and y values. Remember, that's what an ordered pair represents, an x value with a y value. So I can plug that in for x and y in my function to solve for a. So that's what I'm going to do now. I'm going to plug in 0 for y, and I'm going to plug in 0 for x. And now I only have one variable in my equation, so I can solve for that. Remember to follow order of operations as you're working. So I'm going to start inside parentheses. 0 minus 50 is -50. -50 squared would be 2,500. So I have 0 equals 2,500 a plus 75. But this is just a linear equation that we're trying to solve. So we're going to move the 75 to the other side. So we have -75 equals 2,500a. And then we'll divide both sides by 2,500. And we get a to be -0.03. So I found my lead coefficient. Now I'm going to take this number and plug it in for a so that I have my actual equation, my fully formed vertex function. So this would be y equals -0.03 times x minus 50 squared plus 75. There's my function. Now I can use my function to figure out where does my kick land. So I'm going to go back to my calculator. And again, I'm going to make a new page here. If you want to delete the graph like I did last time, or edit the graph, that's fine too. And then I'm going to graph my function. So -0.03 times x minus 50 squared plus 75. So again, I'm only seeing a part of my graph here. So I'm going to adjust my zoom a little bit. Menu, zoom. I think if I just zoom out a couple times, we should be okay. There we go. Do one more for good measure. Okay, so here's my kick, right? Here's my graph of my kick. I know that the uprights are 105 feet away from where my kicker was standing. So they should be over here somewhere, right? Here's my kicker. Over here is where I'm trying to get the ball. Let me put this graph away for just a second. And what I want to know is what's the height of the ball when it reaches the uprights. Since I know the uprights are 105 feet away from my kicker, what I want to know is what's the y value, right? What's the height? That's the y value. When my x is 105. So 105 feet away, where's the ball on this path, on this trajectory? So just like we did with our baseball example yesterday, I'm going to go back to my graph and do a trace to figure out what's the y value when my x is 105. I'm going to bring my graph back up. I'm going to hit menu, trace, and we're going to do a graph trace. And I want to know what's the y when x is 105. And I get the y value down here to be -15.8. You just type with your numbers on your keypad. Yeah, you just start typing. You don't have to do anything special to get that little box to pop up. You just type in the number that you want for x. Okay, so our y value is negative 15.8. So we're talking about somebody who's kicked a football, and now we're saying it's negative 15.8 feet is the height of that football. What would that mean for our problem? It's, well, if we just talk about the height that I've got right here. It means that the ball hit the ground and then tunneled under the field, right? It tunneled 15, almost 16 feet under the field. Is that a thing that happens in football very often? Or like ever? No. So they don't have to like stop the game, dig the ball out, fill the hole back in. Could you imagine how long a football game would take if they had to dig the ball out of the field every time? It'd take forever. So in the context of our problem, this doesn't make any sense, right? What do we actually know happened? It hit the ground over here, right? It hit the ground before the uprights. So you actually answered the next question for me just a second ago. But if we talk about where is the ball, what's the height of the ball when it reaches the uprights? The height of the ball is going to be 0. It's on the ground, right? It actually hit the ground a little before. So the ball hit the ground before it got to the uprights. So did they make the field goal? No. Questions for me for today? Okay. You have no new homework for today. Instead, again, if you have anything that you're missing, I would like you to work on that. I want you to get those assignments in before the end of the school year. For the next couple of days, we're going to alternate working on some review and working on some more practice for our application problems, and we're going to revisit quadratic formula. The kind of tricky thing about our application problems is that every problem is unique. So when I solve by factoring, or I solve by square root, or I solve by completing the square, we have a general idea of our strategy going into those problems. But when we talk about quadratic applications, I'm looking for something different every time. So maybe I'm looking for the vertex. Maybe I'm looking for x-intercept. Maybe I'm looking for a unique point on the graph to be able to answer a question. So we're going to do some more practice with these in the next